Okay, so when we run a simulation, we're trying to model something that's a real-world event without actually having to do the real-world event. Maybe because it's too expensive or we don't have the capacity to get the information that we need. We have to only know percentages of things that exist, percentage of what can happen in a problem situation. So we're looking at an example from the Chapter 11 homework that corresponds to the reading of the chapter about the boxes of cereal with the pictures of the athletes in them. So we still have 20% of the cereal boxes with Tiger Woods pictures, and 30% have Lance Armstrong pictures, and the other 50% have Serena Williams pictures. And so a component of this simulation is going to be picking a box of cereal and seeing whose picture is in it. It's the simplest event that could possibly happen. So we want to choose a box of cereal. And we want to see whose picture is in that box of cereal without actually having to go to the store and buying the cereal. So when we choose a box of cereal, we need to know what picture is in it. So that's the model part, how we're going to model the outcome of choosing that box of cereal. So how do we model which one is a Tiger picture, which one is a Lance picture, and which one is a Serena picture? So we've got 20% of one, 30% of the other, 50% of the third one, which adds up to 100%. If we had 10 digits, 10 numbers, then we can split those up into percentages. For example, there are 10 single-digit numbers that exist. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. If we let 2 of those be the Tiger Woods pictures, and 3 of those numbers represent the Lance Armstrong pictures, and the other 5 represent the Serena Williams pictures, then we can accurately reflect the percentages of the numbers that correspond to the percentages of pictures in the boxes. So maybe I'll let a 0 or a 1 represent a picture of Tiger. A 3, 4, or 5, nope, I gotta go back. 2, 3, or 4, which is 3 out of 10 digits, so that's 30% of the digits. 2, 3, or 4 represent a Lance picture, and the rest, 5, 6, 7, 8, 9, 5 through 9, represent a pic of Serena. So 2 out of the 10 numbers, 3 out of the 10 numbers, and 6 out of the 10 numbers, or sorry, 5 out of the 10 numbers, which correspond to 100% of all the possible pictures that we could get. Now, to make a trial, we have to go to the next step, and that's to put the components together to get a full bank of what we're trying to collect. And according to our original problem, we're trying to buy 5 boxes of cereal and see how likely we are to get a complete set of pictures. So a trial will consist of buying 5 boxes of cereal. That means we have to pick 5 numbers. So a trial is to choose 5 numbers. And that's all we need to know. It says include a stopping rule if necessary. We don't really need a stopping rule here. You pick 5 numbers and you quit. After you choose those 5 numbers, you look to see whose picture those 5 numbers represent, and you're trying to measure whether or not we get a complete set. So the response variable is actually, do we get a complete set of pictures? So it's really a yes or no question, or a complete versus not complete. So we could use C for complete, N for not complete, if we want to use that as a notation. Alright, so we're going to run several trials. If we have multiple lines of random digit numbers, it's easiest if we use a line per trial, but you can keep going in the same line if you don't have enough numbers to use otherwise. So we're going to go for trial number 1. And we'll pick our first picture. So we pick a 7. 7 is a picture of Serena, so I'm going to stick an S over there. And so I don't have 5 pictures yet, so let's pick again. 6 is a picture of Serena. And then a 7 is a picture of Serena. A 5 is a picture of Serena. And a 4 is a picture of Lance Armstrong. So I chose 5 boxes of cereal by choosing 5 numbers. I got 4 pictures of Serena, 1 of Lance, and I'm going to measure my response variable, which is, did we get a complete set of pictures? So my response is, it's not a complete set. Or I could just say no and keep up with how many yeses and nos I get. Okay, so let's try again. Trial number 2, we'll use the second line. So a 0 is a picture of Tiger, 7 is a picture of Serena, 8 is a picture of Serena, 8 is a picture of Serena, 4 is a picture of Lance. End of the trial, we normally do a longer, thicker line to separate off those numbers. Okay, in this case we got 1 of Tiger, 3 of Serena, 1 of Lance. So it means we got 1 of everybody. So that one actually was a complete set. Trial number 3. 2 is a picture of Lance. 5 is a picture of Serena. Another picture of Serena. 4 is Lance. 8 is Serena. End of that trial. That's not a complete set. Okay, we got room to run one more, so we'll go ahead and do one more. So trial number 4. 4 is a picture of Lance. 1 is a picture of Tiger. 2 is a picture of Lance. 3 is a Lance. 0 is a Tiger. Didn't get a picture of Serena that time, so that's another set that is not complete. Now, in the real world, if I were a practicing statistician running simulations to try to make a decision about some variable, I would run hundreds, if not thousands, of repetitions of these trials. And because it's so time-consuming, as a practicing statistician, I would do that with a computer program that could run thousands and thousands and thousands of trials very, very quickly. And then I would just analyze the results when it's finished. Since we're running these by hand, we'll just do enough to kind of get the idea of what's going on and then summarize. So we're going to collect and summarize the observations. So we had 1 out of 4 was a complete set. So our summary really is going to be about how our simulation made our response variable look. So we're going to state a conclusion. There's 2 things that need to always be in the conclusion. One is the fact that your results are based on a simulation, based on a model. In the real world, you could go out and buy boxes and boxes and boxes of cereal, and you may never get these same results. So we want to make sure we start with, according to our model, or you can say according to our simulation, but model's a shorter word, so I like that one. According to our model, only 25%, let's see, how was it worded? We want to make sure we repeat their worded back to them. How likely are you to end up with a complete set? Let me stick in the word there's only a 25% chance of getting a complete set of pictures. And the fact that we said according to our model indicates to whoever we're communicating with that we know that in reality I could probably go out and buy boxes of cereal and not get 25% at all. I might get 30%, I might get 50%, I might get 10%. 25 is just according to this particular run of the model. If we ran it hundreds and hundreds and hundreds and thousands of times, we should get the same results in the very long run as we would get if we bought lots and lots and lots and lots of boxes of cereal in the store. It should be closer to what's really going to happen. Okay, on the next page.